Okay, so today we're going to take a look at some applications of the derivatives that we've been learning so far in this unit. So we're going to talk about circuits, things like, basically like all of the different types of applications that we talked about in grade 12 advanced functions. So we talked about like anything with periodic motion. We can also take a look at like swinging pendulums, things like that. So anything that's a repetitive motion. We can also apply derivatives to these things to find maximums and minimums and things like that. So in this case, we're going to look at a power supply. It's delivering a voltage signal that consists of an alternating current component and a direct current component. T is going to be time in seconds. V is the voltage in volts. I think I missed the V part of this. Where T is time in seconds, and V is, you can add that in, and V is the voltage in volts. And our function is going to be V at T. So it's going to be 5 sine T plus 12. What are the maximum and minimum voltages, and at what times do these occur? Okay. There are a couple different ways that we can solve questions like this. I'm going to show you the calculus way to solve this. You also might see me in the solutions for the worksheets use a little bit of advanced functions information, so I'll touch on that in this example as well. All right. As interesting as it is that the car is parking outside, let's just focus in here. Are they having a hard time parallel parking?
Drug deal going on.
That's what happens when you don't know how to drive. All right.
Hey, Chris, you don't call me out.
Okay, so I have a formula for voltage. I'm looking for maxes and mins. What can help me find maxes and mins when we think about calculus? Okay, so let's find the first derivative of this. Using the constant multiple rule here, we know that the derivative of 5 sine t is just 5 cos t. The derivative of plus 12 is just 0. And to find maxes and mins, we want to set our first derivative equal to 0. Okay, so I provided you guys with, at the beginning of this lesson package, a little kind of like decision-making process that we use when we're solving trig equations. So I'm just going to hop to that for 1 second here so we can see. Okay, decision-making process when we solve trig equations. When we go to solve trig equations, we first look and see if we can use the graphs of sine and cosine. These can be very helpful just to get some quick answers. And wherever possible, we'll try to leave our answers in exact radian values so that when we look for more precise answers, we can use those to calculate other things, right? So if we potentially have to use these for a second calculation. So if you have sine or cos equal to 1, 0, or negative 1, we usually use the graphs for this just to figure out where they are, use the key points. If you have something that comes from a triangle, so a pi over 6, a pi over 3, and a pi over 2 triangle, so ratios from those things like 1 over 2, root 3 over 2, stuff like that, we can use triangle. And then the second triangle is your pi over 4, pi over 4, pi over 2. So if it's like a 1 over root 2 or a 1 over 1, we can use that. When in doubt, if we've tried all these things, we use our calculator. Okay? So let's take a look back at what we're doing right now. So here I have 0 equals 5 cos t. I'm actually going to divide out the 5. It doesn't impact where the maximums and minimums are. So I have 0 equals cos t. If we use that decision-making process that I just scrolled to, when I have cos equals 0, I can use the graph of cos to find the values really quickly. So we're going to use the graph of cosine. Just one cycle, and then we know that it's a periodic function, so if we need to, we can extend the cycle. So where is cos t equal to 0? This happens at pi over 2, this is pi, and this is 3 pi over 2. So these are happening here. Some of these will be maxes, some of these will be mins. So here t equals pi over 2, 3 pi over 2. If we continue the pattern, 5 pi over 2, 7 pi over 2, and so on. Okay, now each of these could be maxes or mins, right? We just found critical numbers. So all of these are critical numbers. We don't know which ones are maxes and which ones are mins at this point. So we have a couple options at this point. I can figure out which of these are maxes and which of these are mins by doing like a first derivative sign chart. I can do a second derivative test and check concavity. I could also just calculate the voltage and see which one's higher. So let's just try that. You can for sure. I don't know if it's worth your time to do a test. If I have a higher voltage, of course that one's going to be the maximum, and then if I have the lower voltage, of course that one's going to be the minimum. What? Sometimes it will ask you like for the first time which that occurs, so you would just be focusing in on these like first times here. Okay, so the first one, we'll see whether this gives us a maximum or a minimum. So we should get 17 volts from this. Let's try 3 pi over 2. What'd you guys get? You should get 7 volts. So I can, because this is a periodic function, it's always alternating back and forth between max, min, max, min. I can assume that the maxes, of course, max of 17 volts, that means this one's obviously the maximum, and this one's going to be your minimum voltage. The maxes are occurring when time is equal to pi over 2, not 3 pi over 2, but 5 pi over 2 after that. And then after 7 pi over 2, that will be 9 pi over 2, and so on. So leave yourself a little space there. We're going to make kind of like a summary of that. And the minimums are happening at 3 pi over 2, 7 pi over 2, 11 pi over 2, and so on. And this is in seconds. Right? Yes, time in seconds. Okay, so I want to make a little statement that basically says that the maxes are occurring at pi over 2, 5 pi over 2, 9 pi over 2, and so on. So we need to create kind of like a general statement for time that tells all of these potential times. So here's how you create these statements. Start with your first one here. The first is pi that we start with. And then figure out what you're adding to get to the next one. So what do I add to get, just focus on the numerators right now. Don't focus on the denominators. Okay, we're adding, not 4.
4 pi.
We're adding 4 pi every time. So we add multiples of 4 pi k, and it's over 2, right? That's the denominator. So this is in seconds, where k is an integer value, so we're going to say k is from the set of integers, and k is greater than or equal to 0, because of course time cannot be negative. So this is from the set of integers, which basically means whole number values. So it's like, it can be negative, positive, or 0, but it's not decimals, so it's just whole numbers. Okay, for the minimum, start with what you're starting with in your list, which is 3 pi, and figure out what it is that you're doing to get from 3 pi to the next numerator. So what are we adding to get to the next ones here? Okay, we're adding multiples of 4 pi, so it'll be 4 pi k, and the denominator is 2. Okay, and this is in seconds, and again, k must be an integer value. If it's a decimal, that kind of throws off the entire thing. And time can't be negative, so we want k to be greater than or equal to 0. Okay, so our maxes occur at all of these potential times here. That little statement that we just created covers all of them, covers them to infinity and beyond. And the minimums are occurring at our little statement for time there, 3 pi plus multiples of 4 pi k all over 2. Okay, and then of course our maximum voltage is 17 volts and our minimum voltage is 7 volts. Okay, part B, determine the period, which is represented by capital T in this case in seconds. Determine the frequency in hertz and the amplitude, capital A, in volts for this signal. Okay, so let's do part B here. Okay, so we're going to take this back a little bit into advanced functions and functions. When we're calculating the period of a function, the period of a function can be calculated using 2 pi divided by the k value of the function. So if our function v at t is 5 sine t plus 12, the k value is usually like the multiple that's inside of sine or cosine. So what is our k value here? No.
5.
1. The multiple in front of t is 1. Okay, 5 is the a value. It's like the amplitude, though it helps us find the amplitude. So here we're doing 2 pi over 1. So for the period here, we're going to get 2 pi seconds. Okay, frequency, we actually didn't do this in, so we said period was going to be represented by t, so I'll just put t here. Frequency, we didn't do this in advanced functions, but our frequency is going to be equal to 1 divided by the period. So in this case, if we're letting capital T represent the period, you're going to calculate frequency by doing 1 over t. So this one's going to be 1 over 2 pi. And the question tells us that frequency here for this circuit is measured in hertz. So that's capital H lowercase z as the short form. Okay, and then again, amplitude. This is taken back from advanced functions here. Your amplitude of your function is going to be the absolute value of the a value in your function. So the a value is this multiple that's out front. So it's going to be the absolute value of 5. And the question in part B also tells us that amplitude is measured in volts. So this will be 5 volts. Absolute value means that everything becomes positive. So if the a value happened to be negative, we just want to take the absolute value of that, making it positive, and then our amplitude will be positive 5. I also should have mentioned that there's extra space on the next page for you guys. Sorry. Any questions on that one? We're good? Okay, let's go to the next one.
I feel like the next one's going to be harder. Oh yes, isn't that drop of physics? Drop of physics. So I dropped it because actually I saw the ending.
Okay, so for small amplitudes and ignoring the effects of friction, a pendulum can be an example of what we call simple harmonic motion. So it's a motion that can be modeled by sine or cosine function, so we call these sinusoidal functions. And it will have a constant amplitude. So of course, if we ignore those effects of friction, we're kind of assuming that the pendulum is swinging without kind of like coming to a stop, right? So it's swinging back and forth constantly and returning back and forth to its original positions, kind of like a metronome does. So the period of this simple pendulum depends on the length of the pendulum. So if if something's hanging down, we're looking at the length of how far that is from its kind of like fulcrum point. And we're going to use the relation t equals 2 pi times the square root of the length in meters over the acceleration due to gravity, which is 9.8 meters per second. Under these conditions, the horizontal position of the bob as a function of time can be described by the function h at t equals a, where a is the amplitude, times the cos of 2 pi times little t, which is time in seconds, over big T, which is this. Okay? Yes, so you have to put that into the function. Okay, find the max speed of the bob and the time at which this first occurs for a pendulum having length of 1 meter and an amplitude of 5 centimeters. Okay, so the first thing that I'm going to find is this capital T. And there's one thing in this that never changes, which is the G part of this. It's always 9.8 acceleration due to gravity. And we want to make sure that we enter in length in meters. So if you weren't given the length of the pendulum in meters, you would have to switch that into meters. Okay, but we are given it in meters here, so we're going to put 1. So let's just make a little approximation here. You guys can enter that into your calculator. What'd you get, Michael?
I'm not sure if I got it right. 2.007 point.
In calculus, we use 9.8. I know in physics, you guys are all about the 9.881, but. All right, Michael, what'd you get?
I got 2.007089923.
Okay, so this is very, very, very close to 2. So I think we're just going to say this is approximately equal to 2. So when we plug this into our h at t formula here, h at t is going to be equal to the amplitude of 5, that's capital A, so 5 cos of 2 pi t. And we've approximated capital T in this equation here to be 2. Okay, if you want to be super accurate here, you can leave like 3 or 4 decimals if you want.
Oh, wait, Mr. Killis.
Yep.
Were we changing amplitude to meters?
No, amplitude is basically just,
Centimeters.
yeah, you can keep amplitude in centimeters. You don't have to switch it. You just need to make sure that length of your pendulum is in meters.
Oh, okay.
Should the question technically specify that the amplitude should be in centimeters?
Amplitude is essentially just telling us like the distance from the middle to the max or the middle to the min. So when I put this in and I get out, let's say, a speed, if my amplitude was put in as centimeters, then I'm going to say it's centimeters per second. If I put my amplitude in as meters, then I will say meters per second. So I can account for that once I do my units of measurement after. So it's okay to have that in centimeters. Okay, so for simplicity's sake, we've rounded this to 2. And we have an equation 5 cos of pi t. Okay, so find the max speed of the bob and the time at which it first occurs for a pendulum having length of 1 meters. Okay. So I'm going to kind of show you guys like a calculus method here, and then we're going to talk about how we can use some of our advanced functions knowledge as well to do some of these questions. So if I'm looking for maximum speed, I am interested in the velocity function, which I will find by doing h prime. So this is going to give us, using the constant multiple rule, negative sine of pi t. And then you need to multiply by the derivative of pi t, which will be pi. So we'll get negative 5 pi sine of pi t. Okay, so this is our velocity formula. I want to find max velocity. So what do I need?
Critical point.
No, that's going to give me maximum displacement. We need to find the derivative once more. Okay, so that will give us negative 5 cos, or negative 5 pi cos of pi t, times the derivative of the inside, which is pi. So I will get negative 5 pi squared times cos of pi t. And that is what I'm interested in setting equal to 0. So I need the derivative of my velocity function if I'm trying to find a maximum of that. Okay, so this is just a number. I can actually divide that out. It doesn't impact where maximums and minimums are.
So is that 0 equals cos pi t?
Yep. And when we're solving equations like this, it can be sometimes helpful to do a little let statement. So let pi t equal x, and then just focus on solving for where cos of x is equal to 0. And then we'll sub back into that let statement. If you feel like you could do this without doing a let statement and just observing where the graph of cosine is equal to 0 and then just sub it into pi t, you can do that. But this can sometimes simplify it for us a little bit. So we actually figured this out in the previous question, but let's just show the graph here. Where is cos of x equal to 0? Pi over 2, 3 pi over 2, and so on. Okay, now this one asks the maximum speed and at which time that first occurs. So we're only really interested in some of our initial times here. We don't need to really like create a statement that says like maximums occur at all of these times. So one of these two is going to be a minimum velocity, and one of these is going to be a maximum velocity. We're really just looking for max speed, so we're actually not really interested in the displacement of that. So really, it shouldn't really matter which one we use, but if we were asked to find maximum velocity, then it would matter which one's the maximum, which one's the minimum. So I will show you guys kind of like which is the max, which is the min, that kind of idea. But we do need to sub these back into our let statement before we go ahead and do any more with it. So if pi t equals x, then t equals x over pi. So if I take each of these and I divide them by pi, we're just going to be left with half, 3 over 2, 5 over 2, and so on. Okay, you can do a second derivative test here. You could do a first derivative test like sign chart to see which ones are maxes and mins. I think we can also just put these into the velocity function and see which ones give us out maxes and mins. So let's evaluate these guys using our velocity function here. And we're really only interested in the first time that this happens. So again, if I'm interested in all the times that give me maximums and minimums, I'm interested in continuing this list. But I'm really only interested in those first times when this is occurring. So we're just going to evaluate the first two here and see what we get. So you're going to apply this formula over here.
Still pi times half.
Yep. So I believe for the first one, you're getting negative 5 pi, because the sine of pi times a half, the sine of pi over 2, in other words, is 1. So this would be, because we had our amplitude in centimeters. This is centimeters per second. So this is kind of like approximately, let me just calculate here. This is approximately equal to negative 15.7 centimeters per second. Now, we also know that we're really just interested in the maximum speed. So even if we calculate this one, we are getting positive 5 pi centimeters per second, which is approximately equal to 15.7 centimeters per second. We're not interested in direction here, though, if we talk about speed. So what is the first time that the maximum speed occurs?
1/2.
So 0.5 seconds, and it is 15.7 centimeters per second. Another maximum speed also occurs at 1.5 seconds, but it's not the first time that it occurs. Now, if I were asked for maximum velocity, how would my answer change?
Well, then you'd have to use, yeah.
Pardon, Anita? Yes, if I was asked for maximum velocity, then we would say occurs at 1.5 seconds.
Velocity is
Okay, minimum velocity is this guy. Speed does not take direction into account. So if we say speed, speed is a scalar. We're just interested in the number itself, regardless of the positive or negative.
okay, so for velocity, you do care about direction.
For velocity, we do care about direction. So this would be like what we call a minimum velocity, and this one would be our maximum velocity. Okay, quick little advanced functions information here. With advanced functions, we actually could use this formula to determine maximum and minimum. So if we look at the formula that we have here, or sorry, we're looking for maximum of this. So if we look at the formula that we have here, maximum is actually equal to the C value plus the absolute value of the A value. So I can actually find a maximum velocity. I can figure out what that is if I simply take 0 and I add the absolute value of negative 5 pi. And that will actually give me 5 pi. Okay, that's maximum velocity, right? We're looking for maximum speed, so it changes things a little bit. And I can also find minimum by doing C minus that. So we will actually get 0 minus the absolute value of negative 5 pi, and we'll get negative 5 pi. So this is centimeters per second for both of these. So I can find those with advanced functions pretty quickly. It took us like a little while to figure those out. We had to do like a whole calculus thing over here to find those maximums and minimums. So I definitely can use calculus. Of course, I can use the advanced functions material as well, but we do need to use calculus to find the velocity function to begin with here. So that is the calculus element of it. So I can use both of these, and I could have, after I found these velocities, I could have plugged them in to the velocity formula here and then isolated for t. So basically how we would do this, I'll show you guys below, because I do use this in a solving process in the homework solutions. Yes, essay? No, you can do this for any trig function.
Just to be clear, when we use marks, we use the advanced functions part of the test.
No, you will have to use calculus anyways, because you have to find the velocity function. So it's not that you're not using calculus. Okay, so if you figured out your max was 5 pi centimeters per second, and you figured out your min was negative 5 pi centimeters per second. If you didn't do all that calculus stuff, like let's say you were at the point where you have the velocity function, it was negative 5 pi sine pi t. We would set the velocity equal to these maximums and minimums. I would suggest that you do both, because since we're looking for speed here, we're actually not interested in the direction. So I would suggest that you solve both, just so that you can ensure you get the right answer for when speed is at a maximum. So let's say we're solving for the maximum here. You're going to solve for the time when that occurs. So really, it's kind of like the opposite of what we just did with calculus. With calculus, we found the times first, and then we plugged them into the velocity function to figure out the maximum and minimum velocities. Here, we find the max and min velocities, and then we have to solve for the times that make that happen. So you're going to divide out the negative 5 pi. You will get negative 1 over here. So you're going to see that we end up with some of the same values here. If you do a little let statement, we're solving for where sine of x is equal to negative 1. So you still kind of have to go through the same solving process, either method that you use. Where does sine pi, or where does sine equal negative 1? What's this value here? This is pi over 2, pi, 3 pi over 2. So here, x equals 3 pi over 2, and then you sub back into your let statement. So you divide out the pi. So you get 3 pi over 2 seconds, or sorry, 3 over 2 seconds. Okay, and then you would also solve for the minimum as well. In this scenario, so you would put in negative 5 pi, you divide that by 5 pi, and then you'd be solving for where sine of pi t equals 1. So we can also use the graph for this, if you do a little let statement. Looking at the graph over here, where is sine equal to positive 1? Pi over 2, so, and then we sub back into the let statement. So if x equals pi over 2, we divide out the pi, we get 1/2 seconds. So these are where our first maximums and minimums are happening. So you see that we basically solved, we got two of the same things. We found that the maximum velocity and the minimum velocity were 5 pi centimeters per second, negative 5 pi, just like we found here. And then we still had to do this kind of similar solving process to get our times. So you can choose whichever method you feel like is a little bit easier. We save the time basically in this one little step right here, which is we don't have to find the derivative after that. So if that's helpful for you, you can use that method. You'll see me kind of use this method just to save myself from like having to find a second derivative and having to calculate. Okay?